Good morning and welcome to this the lecture number 36 of the course Water Resource Systems, Modeling Techniques and Analysis. We have been discussing now the fuzzy optimization techniques. Recall that the fuzzy optimization is especially useful when you want to impart some latitude in the decision making, flexibility in the decision making, and also in situations when you want to address the conflict in decision making. For example, when there are a number of stakeholders, each one specifying his or her own preferences of solutions, how to what degree is the solution acceptable to the particular stakeholder, and these preferences are often conflicting with each other. In such situations, we use the fuzzy optimization techniques. And in the last lecture, I specifically introduced the water quality control problem, where we are dealing with the optimal fraction removal levels or the optimal treatment levels to be provided at individual discharges. By discharges, I mean either the industrial discharges or the municipal and municipal discharges who discharge the effluents into the stream to make use of the assimilative capacity of the river. So, the conflicting objectives there in such a problem are the ones related with the discharges themselves, who would prefer to minimize the treatment level or minimize the cost of the treatment, and those due to the pollution control agencies who would like to maximize the water quality at several checkpoints, which means that they would like to maximize the treatment level. This is over and above the standards that we are talking about. That means, even when the standards are met, whether the water quality at a particular location is acceptable or not is the condition, is the situation that we are looking into. Now, in the last lecture, we introduced this problem. We will quickly go through the problem statement. These are the streams. There is a tributary here. So, this dotted arrow indicates the river flow. So, the dotted arrow is the river flow, and then the dark arrows indicate the point sources of pollutants, the discharges, and then in addition you may also have a non-point source pollution which may be contributing to the stream all along the length of the stream. And recall that these non-point source pollution can be because of the overland runoff that is contributing to the stream all through the stream length. Then you have the checkpoints. So, these are the checkpoints, water quality checkpoints, at which you would like to maintain the water quality at acceptable levels. The desirable water quality at one point may be different from desirable water quality at another point, depending on the type of use that you envisage, the location of the checkpoint itself, and so on. We divide this into several river reaches, 1, 2, 3, etc. Depending on the type of water quality simulation model that you are using, you need to discretize the stream system into several reaches, and in general a particular reach will have one discharger at the beginning of that particular reach. For example, you look at reach number 1, D1 is a discharger, reach number 2, D2 is the discharger, etc. So, you will have one discharger at the beginning of that particular reach. Now, you have the goals of the pollution control agency as well as the goals of the dischargers. Now, the goals of the pollution control agency or the PCA is related to the water quality indicator, and we are in general denoting the water quality indicator by the index I. So, this can be DO or it can be DO deficit and so on. if it is DO, we will say if it is an indicator such as a DO, which will be reflecting the higher the water quality, the better it is. Higher the water quality index value, the better it is. Now, that is what is reflected by such membership functions. And we have on the other hand the preferences of the dischargers themselves. So, these are the membership functions for the dischargers. And these membership functions are related with the treatment levels. So, X here indicates the fraction removal level or the treatment level. Now, I is the water quality index. So, we are relating the treatment to be given to the given at discharger M for the pollutant N to enhance the water quality index I, water quality index value I. So, that is why we indicate this as XIMN. I is the water quality indicator, M is the particular discharger. So, in this particular case D1, D2, D3 etc., DM, and N is the particular pollutant. Remember, the type of pollutants that we are talking about in this example are non-reactive pollutants. Which means the effect of these different pollutants at a particular point location for the water quality indicator I are additive. The effects are all additive. So, they do not react with each other. Now, in this broad framework of the problem, then what are we looking at? We are looking at the optimal fraction removal levels XIMN at all these locations, such that the water quality at several of these locations given here indicated by the water quality checkpoint L is maximized. And therefore, for the water quality indicator, we will have membership functions such as these, which reflect the premise that the higher the water quality indicator value, the better it is. So, in this particular case, you may have a linear membership function like this or a non-linear membership function like this. And on the y axis is the membership function value, it goes from 0 to 1. Similarly, for the dischargers, the lower the discharge, the lower the fraction removal level, the better it is. That is reflected by this kind of membership functions. Again, the beta IMN here will determine the shape of the membership function. When it is linear, this this index will be 1. Now, as you can see, there will be a large number of such membership functions, because we are dealing with several of the water quality indicators I, several dischargers M, and several pollutants N, and associated with each combination of I, M and N at each location L, you will have a membership function defined. Therefore, there will be a set of membership functions which indicate the preferences or the acceptability of the pollution control agency as well as the acceptability of the dischargers. For example, if the water quality indicator value is here, then the level of acceptability will be to this extent. So, the pollution control agencies are saying that at location L for the indicator I, this is the type of acceptability or the desirability of the solution is what is indicated for the PCA, and similarly for the dischargers, this is the kind of acceptability is what is indicated. Now, in such a problem with large number of membership functions like this, what is it that we are looking for? We are looking for a best compromise solution, or because we are indicating all the goals and the constraints as fuzzy sets, we are looking at the maximized value of the minimum membership function value resulting from the particular solution. Remember why we are talking about the minimum membership function value among all these things, because we are defining the fuzzy decision there. So, the fuzzy decision is in fact determined by the intersection of all such membership function values, and that is what is obtained by minimum of all the membership function values for a given solution. There is another aspect here. We are actually making decisions on the fraction removal levels x. The x at any particular location here, for example, at the decision number discharger number 1, we may determine x 1 for a given I and n. This will determine the water quality at a particular location, or this decision will have an influence on the water quality at any given location. Similarly, the decision at this point will have a influence on the water quality at this location. So, the CIL here, which is the water quality at a particular location, will be influenced by, in general, the decisions that we are taking upstream of that particular point, and therefore, you must have models or means or mechanism by which you will relate the water quality at this particular location with the decisions that you are making upstream of that particular location. And these relationships do exist in elegant mathematical form. We just make use of these relationships and then put them in the optimization problem. The non-point source pollution that is joining the stream or along the length is an uncontrollable source. It influences the water quality at all the checkpoints. However, you cannot do anything about this, but you will have to account for this. What I mean by that is that the mathematical models that relate the water quality at a particular checkpoint with the decisions that you are making upstream of that must also make allowance or must also take into account the non-point source pollution while determining the water quality at a particular point with respect to the decisions that we are making upstream of that particular point. And account for all of these, we formulate this particular problem as a fuzzy optimization problem and determine what is called as the best compromise solution. So, this is what I introduced in the last class. We will see the details of this in the today's class. So, as I said, if you look at the water quality indicator CIL, this is the concentration of the water quality indicator I at location L. Now, this is a additive effect arising out of the non-point source pollution. This is LILMN. Look at the definition. LILMN is the concentration of the pollutant N prior to treatment from the discharger M. This is the controllable source. So, this is the point source. And this is the non-point source. Prior to treatment, which means we are making the decision XIMN. This is the treatment that we are giving, and this treatment we are giving on this LILMN. I is the water quality indicator, L is the location or the checkpoint, M is a particular discharger, N is a particular pollutant. So, it can be used for multiple pollutants. The way it influences CIL is given by a functional relationship which has the arguments as LILMN and XIMN. This is the treatment level. Similarly, from the non-point source pollution, the influence that the non-point source pollution has on the water quality index or the concentration of water quality indicator I at location L is given by a functional relationship. This is the functional relationship. So, what this indicates is that it is a sum total of the effect of the point sources after treatment and the non-point sources on the water quality indicator concentration CIL at location L for the water quality indicator I. Now, these are the number of discharges and these are the number of pollutants. For example, you may have BOD as one of the pollutants, you may have nitrate as another pollutant and so on. So, these are different pollutants. Similarly, here you may have uncontrollable sources, several of them. So, P is equal to 1 to NT is uncontrollable source and N is again the number of pollutant, NP is the number of pollutant. So, what this indicates is a general formulation where we are relating the concentration at a particular location L for the water quality indicator I as a aggregate effect of what is happening to the point sources and the influence of the non-point source as much as the concentration CIL is concerned. When we deal with realistic problems, we may be dealing with only 1 or 2 pollutants, 1 or 2 water quality indicators and so on. So, it will be quite simple when we are dealing with actual situations in terms of the mathematical modeling, but the general formulation will address this kind of a model. Now, typically these are water quality transport models, which means if you have a mathematical model which relates the water quality indicator at a particular location as a function of the discharges that are coming upstream of that, such mathematical models can be used into the optimization model to generate CIL as a function of XIMN, which is the decision that we are making. So, this is the general framework. Now, within this general framework then, now this gives you all the details of exactly what I just now told. Remember here LILMN is what I am saying as the pollutant N prior to treatment. Now, prior to treatment, this is what is coming, you are giving a fraction removal level of XIMN. So, the actual load that is coming is 1 minus XIMN and into LILMN will give you the effect of that on the CIL. So, remember we are talking about, let us say a load of unit load is coming, you are taking out x fraction of that. So, 1 minus x will add to the stream. So, the effect will be felt based on 1 minus x, that is the idea there. And the solution of the optimization model is x star, which is the vector of the decision making vector of I will repeat vector of the fraction removal levels at each of the discharges. There are m discharges x1, x2, x3 etcetera xm, that is the vector of decisions that we are talking about. And we formulate this typically as the fuzzy optimization problem, where we are looking at the maximized value of the minimum membership function, typically interpreted as the maximization of the satisfaction level in the system. So, we are looking at the best compromise solution in the face of the conflict that exists in the system in terms of the acceptability, degree of acceptability of solutions for various stakeholders. By various stakeholders, I mean here there may be pollution control agency goals different at different locations, different for different pollutants, different for different water quality indicators and so on. So, these all of them form a set of membership functions. Similarly, at the discharges you have membership functions which indicate the degree of acceptability to the discharger M for the pollutant N at the for the water quality indicator I, because the treatment level is taking place only at one location. But when the discharger M at that particular location has to decide, his or her preferences would be based on the water quality indicator I and the pollutant N, because that is what is the treatment that has to be given at the particular point. And this decision XIMN is related to the water quality indicator concentration CIL at location L for the water quality indicator I. all of these membership functions now we pull together and then formulate the fuzzy optimization problem and look at the best compromise solution. Let us look at a example now. So, if you recall, the general form of the fuzzy optimization problem can be expressed, we did it in the last class. We will just recall, we are in general saying maximize lambda subject to, in this particular case we may have mu of x greater than or equal to lambda, and you may have let us say mu j of x greater than or equal to lambda, j is equal to 1, 2 etcetera. You may have several of such membership functions. So, if you are looking at the solution x, then you may also have x min less than or equal to x less than or equal to x max. So, this is a general formulation where we are defining the membership function associated with the solution x, and then this particular set of constraints define lambda as a minimum among all the membership functions, and that minimum value we are maximizing. So, your solution x will be such that it maximizes the minimum value of lambda, and lambda is interpreted as the satisfaction level in the system. And the solution that arises out of such a model is called as the best compromise solution. So, we are actually looking at the best compromise solution in the presence of the conflict and the preferences expressed by several players or several stakeholders in the system. We will look at an example and then this should be more clear. So, we will take a simple example of a hypothetical system where we have 9 dischargers, 9 effluent dischargers. We have 23 checkpoints, 1, 2, 3, 4 etcetera, 23 checkpoints. There are 9 reaches associated with each of the discharger. So, at the beginning of every reach there is a effluent discharger. Look at discharger 1, that belongs to reach 1, discharger 2 belongs to reach 2 at the beginning of reach 2. Similarly, D8 is at the beginning of 8, D9 is at the beginning of 9 and so on. The checkpoints here are decided based on the type of water quality model that we are using. For example, the discretization of the stream of a reach into several checkpoints, sub reaches, is based on the type of water quality model that we are using. For example, in this particular problem, we will be dealing with the discharger as the pollutant as the BOD, and the water quality indicator we will use it as DO deficit. So, there are several checkpoints like this. So, we would like to make known our preferences for the optimization at all these checkpoints, and these are the dischargers D1, D2, D3 etcetera are the dischargers. We will, for the purpose of this example, ignore the non-point source pollution. So, we will assume that there is no non-point source pollution. Now, within this problem, within this framework, now we are looking at the optimal treatment levels or the fraction removal levels that have to be given at all of these locations, such that the water quality at each of these locations is maintained to the desirable level. In this problem then, now these are the details that I just mentioned. We will also have the data pertaining to the river flows, effluent flows, etc., are available. Then you will have for example, you are relating BOD and DO. So, you may use the classical Streeter-Phelps equations to relate the BOD and DO at a particular location, that is DO at a particular location with respect to the BOD loads at upstream locations. You will relate using the Streeter-Phelps equations, and the parameters for the Streeter-Phelps equations, which typically change from one reach to another reach in this problem, are also given. So, these are all part of the data. So, from this now we will progress to define the membership functions, the fuzzy membership functions for the pollution control agency as well as for the discharges. The water quality indicator that we are using is the DO deficit. So, what will be the preference for the pollution control agency? It would be to maintain the water quality as high as possible at a particular location, and therefore, the DO deficit should be as low as possible. So, your solution should be such that the DO deficit at a particular location must be as low as possible. Therefore, the lower the better is the goal for the pollution control agency. Similarly, for the treatment levels, the dischargers would specify the goals as the lower the treatment level, the better it is. And therefore, the dischargers will also have their own preferences on lower the better. How are these conflicting now? Because both of them are saying with respect to their argument, the lower the value of that particular argument, the better it is. However, when you look at the particular problem, the dischargers will say the lower the treatment level, the better it is. The pollution control agency will say the lower the DO deficit, the better it is. To make the DO deficit lower, the treatment has to be higher, and therefore, these two are conflicting with each other. Therefore, students often make this mistake. Do not go by the shape of the membership function. Look at the arguments of the membership function and then see how the arguments are conflicting with each other, if they are conflicting with each other. And therefore, in this particular problem, because the higher the treatment level will indicate the lower DO deficit, these two aims, these two goals are conflicting with each other, and therefore, we need to address this conflict in the fuzzy optimization problem and then obtain the best compromise solution. The data that we need, so for this particular example, you will understand if you want to apply to a realistic case study, you should have all the specified data. First is these are the discharges. In this particular case, we have 9 discharges. The effluent flow rate itself is one of the data. That means, you have so much of volume of the effluent flow is coming per day. This is the data. This effluent will have the BOD concentration in terms of milligrams per liter, and this is the type of data. Typically, these are industrial effluents, for example, high BOD of 1250 mg per liter, 525 mg per liter and so on. So, these are typically either the municipal sources or the industrial sources. So, these may be for example, textile industry, leather industry, etc., with very high BOD concentrations, their effluents are reaching the river. Then you also have the DO concentrations, which are related to the BOD concentrations. Then you discretize this into river reaches. As I just said, you discretize these into river reaches R1, R2, R3, etc., R9. So, D1 is at the upstream of R1, D2 is at upstream of R2 and so on. Then you have the stream flow. This flow is stream flow. That is in million cubic meters per day. Then you add the stream flow plus the effluent flow. This is per day, this is per day, but remember this is 10 to the power 4 here, 10 to the power 6 here, and then you get the total flow. Now, these many digits are written because it is 10 to the power 6, and then you are also adding to 10 to the power 4 here. So, this is the total flow that is coming, and then what we are saying is at any particular reach here, we know the total flow. One is due to the stream flow, another added to that is the effluent flow. So, the total volume of flow that is occurring in this reach will be this flow plus this flow, that is what we are saying. And then from this point it takes the time of flow for this total flow to reach the end of the reach is governed by the hydraulics of the system, including the cross sectional area, the slope, the roughness and so on. So, this is the time of flow from this point to this point is what is determined and given here. So, this is the time of flow and that is in days. This time of flow, I repeat, is for the flow, for the total flow to flow from the beginning of the reach to the end of that particular reach, that is in days here 0.316 day. And for the BOD DO problem, we need deoxygenation rate and reaeration rate. These are also given. These can be determined from the data, but we will assume that these are given. Their units are 1 by day, that is day minus 1 here. Then you have the DO concentration, which will also depend on the temperature, which is given here. Typically, it will be of the order of 9 mg per liter. Then we will have the preferences. That means, we will say that anything above 3.5 mg per liter of DO deficit is not acceptable, and we would preferably have a DO deficit of 0, which means as close to the DO level as close to the saturation level as possible. Similarly, here we may want to have DO deficit of 0.5 as desirable and so on, 1 as desirable and so on, 1.5 as desirable, not less than 3.5 is what is acceptable here, what is permissible. So, like this we specify our preferences for each of the reaches. So, at each of the reach we are saying that these are the membership functions. It means that any checkpoint within that reach 1, 2, 3, 4 for this 3, 4 for reach number 2, 1, 2 for reach number 1, 9, 10, 11 for reach number 3, etc. Any of these checkpoints within that reach will have the same membership functions. That is the assumption for this particular problem. So, we have all the data in place. We have the membership functions for the pollution control agencies with respect to each of the location points or each of the checkpoints are specified. Similarly, we will now specify the dischargers preferences or dischargers membership function. Now, as I said, the treatment level that you provide at a particular location for the particular discharger determines the water quality indicator concentration at a location L, and this is modeled by Streeter-Phelps equation in this particular example. Because we are talking about only one pollutant, namely BOD, only one water quality indicator, namely DO. So, the dissolved oxygen at a particular location can be determined based on the BOD loads that are coming upstream of that particular location, and this is determined in the example by using the classical Streeter-Phelps equation. I would encourage you to go through Streeter-Phelps equation to understand this problem, and typically the Chapra book gives the basics of the Streeter-Phelps, and these two papers here will provide you how to use the Streeter-Phelps equation in the optimization problem, in the fuzzy optimization problem. In fact, these two papers also provide you with the recursive relationship of usage of the Streeter-Phelps equation for multiple loads. All right. Now, since only one pollutant and one water quality indicator is there, we will simplify the notation by removing the indices I and N, because I is 1 here only DO deficit and N is only one pollutant, namely BOD. Therefore, we will remove I and N. So, we will denote the DO deficit at the water quality checkpoint L by CL and the fraction removal level for the mth discharger by XM. So, we have only two indicators now, M and L. we have removed I and N. XM are the decisions that we are making and CL is the result of this decision, but we have membership functions as functions of CL for the pollution control agency and we have membership functions as functions of XM for the discharges M. So, the membership functions are, we are actually taking linear membership functions. So, the type of membership function we are taking are like this, I will come to that. So, the membership functions that we are dealing with are like this. As I said, because we are talking about DO deficit, we may say the lower the better and we will put a desirable level for the DO deficit as CLD and a permissible level of CLH. So, I will say this is CLD and this is CLH, which means we are talking about the DO deficit. We are saying that we would prefer to have it lower than CLD here, but anything higher than CLH is not acceptable. Therefore, this is we call it as permissible level and this is a desirable level. So, that is what is reflected by this membership function. Similarly, for the dischargers, we will have a membership function similar to this. We will call this as XML and this we call it as XMM, which means the dischargers will say that we would prefer to have the treatment levels lower than XML, but anything higher than XMM is not acceptable to us. So, this is the membership function associated with the dischargers. Then we will have crisp constraints. These are the crisp constraints. Where we will indicate that CL has to be in fact within this range and XM has to be in fact within this range, because we are looking at the optimal solutions in the presence of conflict. Then of course, lambda has to be it is a membership function finally and therefore, it has to be between 0 and 1. So, this is the problem that we deal with now. Is this a LP problem? It is, because the decisions XM and the CL can be related in a linear form. So, we will relate CL with XM using Streeter-Fels equations and make it as a linear function and therefore, we will be able to put this relationship in a linear form and then solve it using the linear programming problem. So, from the general formulation that I gave earlier, we are using alpha as well as beta as 1, therefore, we are using only the linear membership function in this particular case. Now, we need then the membership function values for each of the discharges as well as each of the reaches. Do not lose sight of what we are doing here. Remember, we are talking about this problem now. So, for each of the reach, we need the membership function associated with the pollution control agency, and for each of the discharger, we need the membership function associated with the treatment level. Now, that is what we are writing now. So, for each of the reach, then we need to define L. At L, you need to give CLD, which is the desirable level, and we need to give for each of the location L the permissible level of DO deficit. Similarly, for each of the discharger M, we need to provide what is the lower limit and what is the higher limit. So, that is what is given here. At each reach R1 to R9, we have CLH as well as CLD 3.5, 0, 3.0, 5.5 and so on. Similarly, at each of the discharger D1 to D9, we have the lower limit as well as the higher limit of the treatment levels. Now, this is goal FM, if you recall what we did in the last class, and this is the goal EL for the location L. The location L in a particular reach, all the L will have the same membership functions. For example, reach 1 may have checkpoints 1 and 2, both of them will have the same membership function and so on. And therefore, we have defined for goal EL. So, what is fuzzy goal EL? It is make the concentration level CL, this is we are talking about the pollution control agency goal, CL at the checkpoint L as close as possible to the desirable level CLD. So, we want to bring it as close to CLD as possible, so that the water quality at the checkpoint L is enhanced at the location L. For example, E3 you look at. So, we are talking about the goal of the pollution control agency for the location 3. Go back to the diagram and see where the location 3 is. Now, the location 3 or the checkpoint 3 belongs to the reach 2, and we have defined the membership functions for reach 2. So, for both 3 and 4, the same membership functions as defined for reach 2 are valid. So, we look at what is defined for reach 2 as a membership function, it is 3.0 and 0.5, and therefore, for goal 3 it is 3.0 and 0.5. The permissible level is 3.0 and the desirable level is 0.5, which means that at location 3 or at checkpoint 3, anything higher than 3.0 is not acceptable, and we would like to have the DO deficit to be lower than 0.5. So, anything in between is acceptable with varying degrees, that is the interpretation. Similarly, now you look at the fuzzy goal of the discharges. The fuzzy goal can be stated as make the fraction removal level XM as close as possible to the aspiration level XLM for the discharger M, that is the fuzzy goal, which means we are saying the lower the better. So, for example, at the discharger 9 you look, go back to the data and see for the discharger 9, we are saying that XM is 0.75 and XL is 0.30, and therefore, this is 0.75 and 0.30. So, like this, for each of the dischargers you define the fuzzy membership functions. Similarly, for each of the location which are 23 in number and which are classified into 9 reaches, for each of the location you define the fuzzy goals. So, you have a set of fuzzy goals associated with the pollution control agencies, which is defined at each of the location. You have a set of goals for the dischargers, which is defined each defined at a particular discharger. So, like this you have a handful of fuzzy membership functions, many of them conflicting with each other, and within this we want to get the optimal solution or the best compromise solution. Now, the results of this model are exactly what we did. We have solved this problem now. This is given, CL is a unknown determined by the decision XM. The relationship between XM and CL is modeled through the Stater-Phelps equation, and therefore, XM is the decision variable. Now, these are crisp constraints. CL is unknown, but it is related to XM. XM is the decision variable and lambda is the decision variable. So, we are looking at that particular set of values of XM, which will maximize the minimum satisfaction level. Lambda is interpreted as the minimum satisfaction level. We are maximizing that particular lambda value here. So, we use linear programming, maybe Lingo or some such simple software you use, and then solve this problem. You will get these as the solution. D1 is 0.64. What it says is that the fraction removal level that you need to apply at D1 is 64%, 70%, 72% and so on. These are the fraction removal levels that come out as the results. And the minimum DO concentration level, Remember, this is not the DO deficit. From the DO deficit, we have converted into DO concentration and then obtained the DO concentration. So, R1 you will have a DO concentration of 9.89, 8.76 and so on. So, as a result of this solution, you will get this particular quality. This is the interpretation of the solution, and this is the best compromise solution in the presence of the conflict among the pollution control agency as well as among the dischargers. Now, we will go to a more simpler, more general problem where we will be often using the fuzzy membership functions. In the case of reservoir operation, you will have storage targets as well as the release targets, and typically in the deterministic optimization, when you are doing the reservoir operation, what you would be doing is you would minimize the deficit of the storage from its target, typically the sum of square deficit plus the deficit arising out of the releases. So, this is how you would have determined the reservoir operating policy. Now, this was a crisp optimization. What we will now do is, we will start relaxing that crisp conditions and then state in terms of the fuzzy membership functions the deviations from the target themselves. That means, the higher the deviation, the worse it is. These kind of linguistic statements we will try to build it into reservoir operation problems and then see how the solutions look at the solutions appear. Essentially, you must keep in mind that we are introducing more and more latitude, more and more flexibility into the solutions by introducing by treating the crisp optimization problems as fuzzy optimization problems. So, first let us look at the crisp problem now. This is taken directly from the classical textbook by D.P. Lokes and others. For all water resource system students, I would encourage them to go through this particular textbook, which is extremely comprehensive. It is almost inimitable style of writing and presenting. So, all of you must have access to this. I understand that this is also available on the net. You may just look for this particular textbook. So, I am taking this discussion directly from this particular textbook. So, we have a storage target and we also have a release target. The reservoir capacity is known. Now, we are looking at maximizing the storage target itself. That means, we do not a priori specify storage target, but we will formulate the problem such that the storage target that can be met most of the time is itself maximized, which means on an average we would like to maintain the storage as high as possible, but the release target will specify and then reckon the deficit as only that particular value of deficit whenever release is smaller, not the other side of the deficit. That is, we will reckon the deficit to be non-zero only when the release is less than the target. We specify the target and compute the deficit as release minus that particular target, and only whenever it is less than 0, we put it as that particular value. Therefore, we take the mod of that particular amount. So, the objective will be to find the highest value of the storage target T s. We are trying to maximize the storage target that minimizes the sum of squared deviations from actual storage volumes and releases less than the minimization release target. That is, what we mean is that we set the target for release and then look at the minimum value of the deficits for the releases from the targets, and then look at the maximization of the storage itself. So, that is the idea here. So, the way we write it in a mathematical form is, for this particular problem we take as 3 time periods. So, we are summing the deficits of storage and the releases. This is the deficit in release, the squares of that minus we are looking at the storage target T s. This is the decision variable. We want to maximize the decision variable T s and therefore, we penalize, because it is a minimization problem, we penalize Ts through a negative value here. What does this ensure? Because we are using a negative value for the penalty, it ensures that the Ts is as high as possible, because we are looking at minimum value. As Ts increases, this value decreases, and because we are looking at minimum value, that will be preferred. This is subject to the storage continuity equation, St plus Qt minus Rt is equal to St plus 1. This is the continuity that we have been talking about all through. The capacity is known, the storage should be less than or equal to the capacity, and the dRt here is defined such that Rt is greater than or equal to Tr minus dRt. TRT is specified. In this particular example, we put it as 25, and dRt is a decision variable which is governed by Rt. So, when you solve this, what is it that we should get? We should get, because k is specified, we should get St, we should get Ts, which is the storage target, and we should get dRt. These are all the decision variables, and there are 3 number of time periods. The inflows are given, Qt is known, and similarly the capacity is given as 20, and there are 3 time periods. So, we will solve this example and then get the solution as this. So, you get a Ts of 15.6, S1, S2, S3 are given, and R1, R2, R3 are given 14.4, 27.5, etc. And this is the dRt that you get as 184. This is the total value of the objective function, which we denote it as d. Now, this is the solution for the crisp problem. What we will now do is, we will convert this into a fuzzy problem and then look at the membership functions rather than looking at the actual values of the target storage. What we will now do is, we will start imparting some latitude into the problem, relax the constraints, and then look at what is the best compromise solution that we are getting. Why we call it as best compromise now? There is a conflict between the release and the storage. The more you release, the less will be the storage. You would like to maintain the storage also high, you would like to maintain the release deficit also low, and therefore, there is a conflict that exists. This conflict now we will model through the fuzzy membership functions and then look at the best compromise solution. So, this is a general form of the fuzzy optimization problem. We are looking at maximization of the minimum value of the membership functions. Now, these minimum values together will define the satisfaction level in the system, and then we are maximizing that particular satisfaction level. So, typically we write this as maximize lambda subject to mu St greater than or equal to lambda for all t, and mu Rt greater than or equal to lambda for all t. So, this is the problem now. So, if you know the membership functions, you solve this problem using this particular objective function and these as constraints, you will obtain the value of lambda as well as St as well as Rt. Now, for the St, look at this membership function now. We are saying that you would like to bring the storage as close to the target as possible. So, we may define a linear membership function something like this. So, from the left when you are approaching, you would like to come as close to Ts as possible. So, we will say St by Ts whenever St is less than or equal to Ts, and as it starts going up, you do not still want it to be very far away from Ts, and therefore, you will write this as the membership function when you have St greater than or equal to Ts. So, this defines the membership function for the storage. What does this indicate? This indicates that the storage, the actual storage value should be as close to Ts as possible. That is what is indicated here. Similarly, for the release, your target is 25, but you would like, don't mind the release to be greater than 25, because recall that we defined the deficit only when release was less than 25, less than the target. Therefore, the fuzzy membership function for this is that you would like to have the release as close to 25 as possible from the left side. So, Rt by Tr, that is this line, and when Rt is greater than Tr, we will put the membership function to be 1, which means that anything greater than Rt is fully acceptable. So, this is the way we define the membership function for the storage and the release, and then solve the problem. When we solve this problem, we will get the minimum value, which is lambda. Actually, in our notation, this is lambda. So, what we are saying is we are maximizing lambda subject to mu s t greater than or equal to T s for all t and mu r t greater than or equal to T r for all t. I am sorry, this is lambda. So, we will write this as this greater than or equal to lambda and this greater than or equal to lambda. Now, that is the solution that we are talking about. As a result of which we get S t for all t as solution, R t for all t as solutions, and the associated value of lambda. So, this is the associated value of lambda. T s we are maximizing, T s is also a solution, that we get to the as 21, and then S 3, S 1, S 2, S 3 and R 1, R 2, R 3. This is the solution. When you are comparing the crisp solution with the fuzzy solution, you must keep in mind the value of the objective function or the values that you actually get here is not so much important. What you should compare, what you should keep in mind is that you have been able to impart flexibility into the solution, and therefore, the solutions are more realistic. You are able to incorporate the preferences from various stakeholders, and these preferences you have modeled using the fuzzy membership functions, and therefore, the fuzzy optimization problem provides you more realistic, more flexible solutions rather than the crisp optimization problems. So, this is what you should keep in mind when you do the fuzzy optimization. So, essentially in today's lecture, we have continued our earlier discussion on the fuzzy optimization. We dealt with the water quality control problem and took a hypothetical example through which we demonstrated the use of the fuzzy membership functions, which indicate in fact the conflict that exists in the system, and then we arrive at best compromise solution when there are several stakeholders or several players in the system, each with his or her own preferences of solutions, and these preferences often conflict with each other, and then we formulate these problems as fuzzy optimization problems, look at maximized minimum value of the acceptability level or the satisfaction level in the system, and therefore, we call this as best compromise solution. Then towards the end, I also demonstrated a simple problem where we are looking at the reservoir operation problem. You would like to maintain the storage to be as high as possible without increasing the release deficit. So, we formulated linear membership functions for the storage, and then looked at maximum value of that particular storage target, and also we formulated linear membership function for the release, and then we use the fuzzy optimization to obtain solutions. I mentioned in the course of the lecture that the fuzzy optimization imparts more flexibility, more latitude in decision making, and therefore, it is more realistic for actual applications compared to the crisp optimization. So, in the next 3 lectures, so the next 4 lectures, I would take up some case studies which apply all the methods or many of the methods that we have dealt with in the lecture so far. So, we will continue the discussion in the next class. Thank you for your attention.